So my question is there some techniques to make our function more maybe convex, maybe quadratic or something like that, just to better optimization, maybe some residual connections in neural network for that.
So okay, we will cover a bit of it in the next lecture. I will mention two examples here. So, the problem is, suppose we have a very deep neural network and our loss corresponds to a simple square error. Yes? And basically we calculate the variance with respect to some wj. This is a vector, this is a vector, and we have many layers in our neural network. Typically, when this W is somewhere in the very beginning, in the first layer or second layer, the value of this gradient would be close to 0 because we backpropagate through it. And also, if you backpropagate back, we accumulate the errors in the gradients. And it's also bad because we have not exact values of the gradients, but rather some approximation to perform an update of the parameters of the system. And many people are thinking on how to improve this issue of neural networks. How should we train deep neural networks? Really deep. At that time, very deep was like 15 or maybe 50 layers. And actually, one example I want to show you now, okay, is a skip connection. Basically, we can say that let us consider a simple layer of neural network. Let it consist of two parts. Let it be input for layer x, and one path is to keep x as it is. It is a skip connection, yes? And another part is some parametric function that corresponds to layer number L, x, and some parametric number L. In this way, we still has the output that is non-linear of the input. But what is more important, when we take the derivative with respect to r plus there, we get the 1. So it still has a big magnitude. And because of this, we improve propagation of the gradients to the first layers of the network. They are still of meaningful size. We will consider some more things on this the next time. Basically, we will introduce two popular neural network architectures, convolutional neural networks and transformer neural networks, and look at how things are performed in them and what tricks they enable to make conversions faster and to make everything convergent.
But it makes our function simpler to optimize.
I suppose yes. We can't prove everything still. Maybe there are some theoretical assumptions that are not that popular, but rather in engineering way, I expect things to become better. Also, another example. Okay, let it be something I will do on Thursday. I still have some space for it, so don't worry, we will cover it. Yes, last question.
There was a slide with comparison of different methods, and the measure was training cost. What is the range cost?
I suppose it's a misprint. And actually, not the training cost, it's the training loss. I will look at this paper, but
the computation which is more efficient.
I would say that pure stochastic gradient descent would be faster because we don't need to multiply everything squared, but basically the difference is not very big. All of them, okay, pretty much the same in terms of memory requirements and computational requirements. We still need to store gradients, we need to store the parameters itself, and in addition, when we have momentum, we need to store momentum, but the amount of memory is linear with number of parameters. Okay, that's all for today. Thank you for joining.